I'm Pavan Balaji. I'm at the Argonne National Lab. I run the programming models runtime systems group over there. I've been tasked with talking about interconnects today. It's going to be a short talk. It's 40 minutes or something. So it's going to be a high-level talk on interconnects and what kind of technology is going on in interconnects. It's slightly higher level than Karen's talk, a little bit further up the stack over there. But hopefully we can give you a little bit of feel of how these interconnects connect to the processing subsystem, the memory subsystem, applications, and so on. All right, so we'll get started. Okay, so we use interconnects everywhere, right? Every computer system, any large-scale systems is connected with interconnects. And every time you are building a huge supercomputer, the first thing you have to think about is how am I going to connect all of these systems together, how are individual computers together, okay? The exascale systems coming up in a few years, they are no exception, and interconnects play a big role in these systems as well. So this is a quick chart from DOE. This is an old chart, a very old chart that DOE has been using it for, I don't know how long has it been, 10 years, something like that. But I updated it with some newer numbers. This is not the exact same chart from the original DOE report. The original chart, the numbers were totally off, so I updated it with what we know for the systems coming up, the coral generation machines and so on. So we are at about 100 petaflops right now. We'll probably be getting to about 200 petaflops soon. And the plan is to get to exascale by around 2021, 2022, around that time frame, okay? The interconnect part is what I want to focus on over here. So first of all, before I talk about the interconnect, there is the node concurrency part that we need to be aware of, okay? So right now we have 30, 60 cores. We are moving to this era of 100 or 1,000 cores per system. And all these cores are going to have essentially a shared network interconnect, okay? The network interconnect is going to be on the node, and all of these cores are going to share that interconnect. That's one important thing that we need to remember. Okay, it's not like a per processor cache or something like that, or registers that sit on each processor. It's all shared. Okay, all these cores have to talk together to these interconnects. There is a lot of node performance. There's an increase in the node performance, which means that all of these cores are able to compute very fast, and they're going to dump data on this network very fast. Okay, it's going to be divided between all these cores. So each core is not faster, but a lot of cores are driving that network. And node interconnect bandwidth is increasing as well. It's going to increase about an order of magnitude going in the next 4 years or so, maybe more. Okay, some people are envisioning that this will go to about a terabyte per second, not 200 gigabytes per second. Okay, so there's going to be a lot of bandwidth, but it's going to be shared across a lot of cores. So one thing to remember is that the expectation is that the increase in the number of cores is going to be faster than the increase in the interconnect bandwidth, which means the amount of network bandwidth each core gets is actually expected to drop, okay? All right, so general trends in system architecture. Number of nodes is increasing, okay? But it's increasing at a moderate pace. It's not increasing that rapidly. This is the number of nodes themselves, okay? So it might about say double by the time you go to exascale from here, okay? It's not going to go up like 10 times or something. The number of cores or threads per node is increasing rapidly. That's the big constraint, okay? That's a big concern. So number of threads or cores are increasing, which means there's a lot more sharing going on the node when you're trying to use these network interconnects. Each core is not increasing in speed or frequency, okay? Each core is about flat. Probably the most controversial part is the chip logic complexity is decreasing, okay? Some people say that it's not decreasing, actually constant or even increasing slightly, but I tend to believe that it's actually decreasing. You have more in-order instructions now, not out of order, no pipelining or no branch prediction, mainly because of the power constraint, okay? Whether that's true or not, it's at least rather flat. It's not increasing, becoming super complex. What does that mean for the networks, okay? For the networks, it means that more cores will be driving the network, okay? I think I made that point already. There's more sharing of the network infrastructure. It's not just sharing of the network adapter that sits on your node, but also sharing of the entire topology. Okay, I'll talk about that also in the next few slides. The aggregate amount of communication from each node will increase moderately. How much data is each node dumping into the network is going to increase moderately, but it's going to be divided into a lot of smaller cores, which means instead of having one core dump in a megabyte of data, you have 1,000 cores dumping in a kilobyte each, okay? Or 1,000 or 10,000 cores dumping in 100 bytes each, or something like that, okay? So they are more fine-grained. There's more fine-grained access to the network. That's the important thing to take away. And a single core will not be able to drive the network fully. Okay, this is already true today. Okay, today a single fast Xeon core will still not be able to drive a network fully. Okay, if you go to Xeon Phi or something like that's or GPU cores or something of that sort, they definitely won't be able to drive a network. Okay, one, the network is faster than what a single core can drive, and two, the network itself has a lot of parallelism. Okay, if a single core is trying to drive the network, you're not utilizing the parallelism, you're not able to get the performance. So in some sense, the networks are designed to be used by multiple cores. If you try to use it with one core, you'll not get the performance. Okay. Okay, so I'm going to give a very simplified network architecture picture over here. This is ancient. Okay, this networks used to look like this 20 years ago. Okay, this is not how networks or systems are integrated today, but this is 20 years ago. Okay, but it's a depiction, or it's an easy to understand picture to see. Okay, this is how we can visualize how a network is integrated into the system. And over the course of these slides, I will show how the technology is improving and what is getting more and more integrated, or what is changing in these architecture. So if you look at this simple architecture, let me move out of the way over here. Simple architecture, we have a bunch of processors. Each processor has a bunch of cores. Okay, these are connected to this bubble thingy over here, which is usually at some point it used to be a North Bridge memory controller integrated thingy. And on other side over here, we have memory. Okay, so each of the processors could access the memory. Okay, it's uniform access to the memory. Now this North Bridge or memory controller would be connected to a network adapter through a I/O bus or some sort of I/O interconnect, like a PCI Express or something. And the network adapter would be connected to a network switch with a network cable, and the switch would go on to connect to other switches and whatnot to form the entire network topology. Okay, this is the overall simplified or traditional, let's say, network architecture. As I mentioned, this is not how current systems are integrated. Okay, but this is how they used to be 20 years ago. And the important thing to remember over here is that when you have these bunch of things, you can't just say that I'm going to buy a fast network. I can't just say that I'll go and buy a fast 100 gigabit per second network or 1,000 gigabit per second network and connect it to my system. It has to be balanced to the rest of the architecture. If I just plug in a fast network, I'm not going to get better performance because all these other subsystems have to improve correspondingly. Okay, and I'll talk about these in more detail, but for example, they are going to be processing bottlenecks. Just because you have a fast network doesn't mean that the core can drive that network. Okay, you should be able to have technology improvements that enable the processor to drive that network fully. There are going to be issues with the connection from the North Bridge to the network adapter. Okay, your PCIe or PCI Express or whatever you're trying to connect, that has to correspondingly increase in performance too. Otherwise, you're just connecting a fast network and not able to get to the network fast enough. Okay. Of course, the network adapter, the actual network performance has to improve too. And finally, the network fabric or the topology of the network has to improve too. Just because you have a fast network that connects you to the topology doesn't mean that you can get to the end host, because the network topology, the switches or the routers, they're all shared between multiple nodes. So you should have a corresponding increase in these as well. So these are four of the things that you need to worry about, and you need to do this in a balanced way. You can't just pick one of them and say, I'll put a fast network. That's not going to help you at all. Okay, you'll basically get the same performance as you were getting earlier. All right, so I'll talk about three things in this talk. The first one is network adapters. These are the hardware, the piece of device that sits on your node. Okay, that the one that you go and plug into your in old days, PCI Express slot or whatever, right? Or on your processor nowadays, the thing that goes on the actual node. That's the first thing I'll talk about. The second thing I'll talk about is network topologies. This is your switches and routers, the rest of the infrastructure, right? Once you go outside the node, before you get to the next node, how are you traversing the network? How are you getting to that node, right? That part is the network topology. I'm going to talk about that a little bit. And at the end, just a couple of slides, I want to talk about the network processor memory integration. It's a very important piece. A lot of people tend to ignore this aspect. You can't just drive the network if it's not well integrated with your processor and memory subsystem. Okay, and we keep talking about this. It's still lagging in many ways, but at least the there is a ray of hope in the future. Vendors are moving in the right direction in how these networks are integrated into the processor and memory subsystems going forward. All right, let's talk about the network adapters. A little bit of history before I talk about network adapters. Okay, so first, the first commercial network adapters came out in about 1979. Okay, this is the Ethernet. This is not the fast Ethernet, the Ethernet, 10 megabit per second Ethernet. There used to be older networks before this. Xerox had the 3 megabit per second Ethernet also, but that was not a commercial thing in some sense. It was not sold separately, so I didn't include that in this list over here. But commercially, the first ones, let's say, are the Ethernet adapters in 1979. Okay. It connected a bunch of printers, let's say, and a bunch of computers, and people were happy for a long time. Okay, 14 years, nothing happened. Okay, everyone was like, oh yeah, I have a network. I can talk to the computer. Didn't matter how fast I could talk. Just the fact that I could talk to the computer was great. Okay, and they worked around that. They were able to design algorithms that were able to use the fact that the computers are connected. That's great. Then around 1993, people realized, oh, suddenly they woke up and like, oh, network is a bottleneck. I can't quite do what I want to do with a very slow network. So there was a lot of activity suddenly around that time, around 1993, and said, okay, I need faster networks. Okay, I can't just deal with a 10 megabit per second network. So fast Ethernet came up. Fast at that time was a 100 megabit per second network. Okay, that was around 1993. And gigabit Ethernet came out around 1995. It took a long time to catch on, but the adapter started coming out in 1995. Okay, and ATM, Mirrornet, Fiber Channel, they all came up with around gigabit per second networks as well. So there was a big activity of, a lot of things are happening, a lot of improvements in the network around that time frame. So around 1993 to 1995, there was a big jump from 10 megabit per second to gigabit per second. Okay, big jump in the amount of network performance, actual network adapter performance that was there. That was many years ago, but after that, the trend of increasing network performance continued. And as there was more and more performance added to the network adapters, people started coming up with more and more ways in which you can use this network performance, the way you can design new algorithms that use this network performance, or way you can connect machines. Okay, if you can connect more machines, you can connect machines in a more complex manner if your network performance is better, or you can design better algorithms if your network performance is better. Recent network technologies give much higher bandwidth. InfiniBand EDR, for example, gives about 100 gigabit per second per link, okay, which means that you can have 8 links and I can have 800 gigabit per second. Okay, that's where we are currently. And multiple network links is not uncommon. If you look at the Coral generation machines, they're already using multiple network links. The Japanese T2K machine is also using multiple links. So it's very common to have multiple network links. Each link can give 100 gigabit per second, but having multiple of these links is not uncommon. But the link speed is also increasing. By the exascale generation, people are thinking of getting to about a terabit per second per link, okay, plus multiple links. Okay, so the network bandwidth is going to keep increasing a lot. The end host peak network bandwidth, okay, what's the maximum you can get, that is, in some sense, is mostly considered a solved problem, okay, because all you need to do is add more links if you have lesser bandwidth. It costs money, okay, but it's not a technological limitation. Okay, in some sense, a technology because you want to make it cheaper, but in some sense, if you have enough money, you can always build it, okay. The other problems that you can't quite solve, like network latency, okay, that you can't just throw money at it, you can't just fix it because it's physics. Okay, you can't improve it after a certain point, like speed of light. Okay, so you are pretty close to getting to that point, right? You are pretty close to hitting speed of light, which means you can't improve it. You can't just throw more money at it and make it faster. Okay, that's a bigger sort of problem. The other things like message rate or congestion in the network and so on, it doesn't improve. These are not solved problems, but I'm just talking about the peak network bandwidth for the end host. That is mostly a solved issue. And we're working a lot on improving these as well. We're not just ignoring this problem, but there's going to be improvement, of course. We're going to improve it 2x, 3x, or whatever over the next, by the time exascale machines come in. But the important thing for you to remember is that there is a limit. Okay, we can't just keep improving network latency. Okay, it's not going to work that way. So if your algorithm is relying on the fact that the network latency will improve, then it's time for you to go back to the whiteboard and redesign your algorithm. Okay, It'll improve a little bit, but there is going to be a wall. We can't just cross that wall, okay? That's something to keep in mind. All right. Okay, so back to our simple network architecture picture. So we had the process, memory, I/O bus, network adapter, and network switch. This is 20 years old, right? In this picture, I mentioned these are all decoupled. Okay, the processor is doing its own thing, the memory is doing its own thing, the network adapter is doing its own thing, and they're all connected with these buses or interconnects or whatnot. Okay, then they have to work with each other in some way. And whenever these are decoupled in this manner, the working together is going to be really complex and inefficient. So the current generation systems, actually this is already like 5 years old at this, or 10 years old at this point, but in about the last 10 years or so, there is an integration that is coming in. So if I can just flip back to the old picture, we have the processor and the memory separately, and this north bridge over here sitting over here. There is a tighter integration that came in about 10 years ago where the memory controller, okay, the cloud bubble that I showed in the previous picture, that memory controller, people started integrating that onto the processor itself. Okay, so you have something like this. You have the processors, we have the memory controller talking to each memory, and each of these can connect to a one or more network adapter through the I/O bus or I/O interconnect. Okay, this is your NUMA architecture. Okay, your memory controller is integrated on the processor itself, which helps with the memory access to the memory, faster access to the memory. Okay, this integration of the memory controller on the processor, instead of decoupling the memory and the processor, they integrated the memory controller on the processor. This integration didn't happen for network purposes. This actually came in because people wanted to optimize memory bandwidth or wanted to increase the memory bandwidth. Though whatever be the reason, this integration helps the networks too. Okay, it improves network communication because there's always a coordination. When you're talking about this previous picture, these two decoupled entities of the processor cache, and the memory, they have to talk to each other and they have to coordinate with each other. That's very complex, and that requires a lot of interaction between those two. The integration that I show over here, that helps in this interaction, it minimizes this interaction, improving network latencies. In fact, with this NUMA architectures, network latencies have improved. The actual network latency as an actual time taken for the data to go from memory to the network adapter have improved about 10-fold by doing this integration, because they're so complex for the cache to coordinate with the memory. I have a few slides later, and I'll talk about how this actual interaction works, but this tighter integration helps with that sort of performance improvements. In this picture, I'm only showing one network adapter being connected. This network adapter can access any memory. You can access this memory too, over going from this processor memory controller to that memory controller, that memory. You can access any memory. It's just it's closer to one NUMA domain, let's say, to one processor than the other. Okay, but everything is accessible from that network adapter. All right. If you take one step further and look at the new, current, but very new systems, or the next generation machines that are coming up, there's even tighter integration that's happening. Okay, so in this, let me flip through. In this, all three were decoupled, right? Older generation. In the current generation, we have the memory controller that is integrated on the processors. In the next generation, or the very new adapters that are coming out, very new processors that are coming out, there's even tighter integration where the memory controller is, of course, integrated, but the network adapter is also integrated on the processor chip. Okay, so the OmniPath, for example, is the Japanese machine that came out. They have this sort of tighter integration of the network. The network adapter itself is integrated on the processor, so it's all integrated on one chip. And that's one part. The second part is that memory itself, at least a part of the memory itself, is being integrated on the processor too. I don't know if Scott's talk already covered that for the some of the newer architectures that are coming out. But there is some part of the memory that's integrated on the processor too. But the network adapter, the memory controller, they're all integrated onto the same chip, which means this interaction of figuring out where the data needs to go from, what caches need to be invalidated, what needs to be done, all this becomes much more tightly coupled, okay, much closer, densely packed in some sense, and that makes it faster to do this sort of coordination. Now, when this first came out, there was a big hype from industry that said, oh, this will improve your network bandwidth a lot. Okay, It's unclear if it will improve the network bandwidth because in some sense with the advances in PCI Express and HDX and whatnot, it is unclear whether that was a bottleneck or not. Okay, so I don't know. So maybe it improved the network bandwidth, maybe not, I'm not sure. But what it does improve is the network latency. Okay, that for sure, because the latency is bound by how much coordination you're doing between the processor and the cache and the memory system and so on, and the network adapter. And if you pack them closer, it's just physics, right? You move things closer, you have to travel lesser distance, which means it improves the network latency. Okay, so that's one thing we know for sure this sort of integration improves with. Another thing, another subtle thing that you might not expect is that it improves network functionality. One example is atomic operations. Okay, networks do their own atomic operations, so you can do a compare and swap on the network. Processors do their own atomic operations. Okay, you can do a compare and swap. These two atomic operations are not atomic together with each other. Okay, processor atomics are atomic with respect to other processor atomics. Network atomics are atomic with respect to other network atomics, right? But when you use both of them together on the same memory location, it doesn't work. It might corrupt data. They're not atomic with respect to each other. This sort of integration allows the network to know the processor a little better, or the processor to know the network a little better. So this allows, in theory, it can allow for better functionality in the sense that your network atomics and processor atomics could be atomic with respect to each other. Okay, so you can have that. As I said, it's in theory. The first generation adapters that came out, they integrated this, but they don't yet provide that functionality. But the expectation is that the next generation adapters are going to improve that function. At least this sets the base. Okay, it sets the requirement saying that here is what I can achieve. Okay, and the next step is to actually achieve that. So current generation don't do, but at least we are at a point where we can think about doing this better integration. All right. Okay, so that was with respect to the network adapters themselves. Let me talk a little bit about the processing. Okay, so just because you have a fast network does not mean that you can get good performance. You should be able to drive the network fast enough. Okay, the processor should be able to issue instructions to that. Okay, it should be able to say, go send this piece of data to that node. It should be able to do that fast enough in order to use the network effectively. Okay, so traditionally, we used to use TCP/IP, UDP/IP, whatnot, and these are essentially generic protocols. And they are slow. They are not able to use these networks fully. Why are they slow? The reason they are slow is because they essentially assume that the network adapter is dumb. Okay, they assume that the network adapter is not capable of anything. And so they emulate everything in the TCP/IP stack itself. Okay, I'll do my own reliability. I assume that the network adapter will not be able to send my data reliably, so I will do my own network reliability. I'll do my own flow control. I'll do my own congestion control. I'll do all sorts of things, right? So because you're doing this, you're essentially making everything redundant, even if the network adapter can do it. That essentially costs a lot of performance. There are other aspects also because of how the kernel is set up, so you have all these interrupt handlers and whatnot, which makes it a little harder too. But broadly speaking, there are assumptions or lack of assumptions in the TCP/IP stack. It's a very generic protocol, which makes it very hard to get performance for these fast networks. If you look at most modern networks, I think none of them use TCP/IP. The only adapters that use TCP/IP is there's a company called Chelsio that sells these adapters which have hardware offloaded TCP. Okay, that's the only company that probably does TCP right now. But apart from that, no one really does TCP on these high-speed networks. Use something else, a different network protocol. And they're spending, all of these network protocols, the common feature in most of these network stacks is that they are going to this mode of what is called as an offload mode. Okay, they want to offload as much functionality as they can onto the network hardware itself. Okay, so the network adapter, the network chip itself is capable of doing a lot of work, including error correction, flow control, congestion control, and whatnot. Okay, so chip itself is capable of doing that, and that's becoming more and more common with most network adapters today. This has been true for 10 years at least, 20 years or something like that, and almost every future network adapter is going to have some sort of support to do hardware offloaded functionality. What the extent of that functionality will differ with different networks, but there's going to be some support for hardware offloaded functionality for most network adapters. And we also have features which allow data to be moved more tightly controlled movement of data from your memory to the network adapter. So just if you compare a traditional TCP/IP stack with your current generation offloaded network stack, here's a quick picture that shows that this is the ISO-OSI model, right? You have this physical layer, network link layer, data link layer, network layer, transport application, whatnot. So this is a traditional TCP stack. So the bottom layer, the physical layer, you have copper, optical, wireless, whatever you want to use. Above that, you have the link layer, that's flow control, error detection, whatnot, Ethernet, let's say. Above that is the network layer, which does things like routing. That's your IP layer. Above that is the transport layer, does your congestion control, does reliability if needed. That's like TCP or UDP. And above that is the application layer, HTTP, FTP, MPI, whatnot. That's your traditional network stack. The newer network stacks are more hardware offloaded, but they have equivalent support for most of this functionality. Okay, the physical layer is copper or optical. We don't use wireless, maybe sometime in the future, but not right now. The link layer, there's a link layer. It's not. Sometimes it's Ethernet, sometimes it's not. Many cases it's not, and they do the similar functionality, right? Flow control, error detection, whatnot. There's a network layer. It's not IP, but it's a network layer. It still does routing. Okay, it's just not IP. Okay. Above that, the transport layer, again, not TCP, but does the same sort of functionality. It does reliability, it does congestion control, things of that sort. And one thing I forgot to mention over here, typically when you use the TCP stack, you're using this sockets interface, Berkeley sockets interface. Over here, you use a different interface. Okay, not sockets, a different interface for these network adapters, because the functionality is very different, and your traditional sockets layer is so tied to TCP/IP or UDP/IP or whatever it is that it's kind of hard to use the features of these newer adapters if you continue to use that API. So these network adapters said, okay, forget it. I'm going to create my own API. I'm going to give you a very low-level API, which will give you a very high functionality. It's going to be a pain in the neck to program with, but it's going to be very fast. Okay, that's the point. Okay, speed, performance, always, right? They didn't care about productivity at this level. Okay, if you want to make it more productive, write higher-level libraries on top of it, right? MPI or PGAS or whatever you want to do. Okay, but this is going to be about performance. So that's that low-level interface that got built, and on top of that, you build these application layers. Okay. Now the thing to remember is that this is very tightly designed for HPC systems. This is built for supercomputing or enterprise data centers or things of that sort. Okay. So these are meant for performance, and you don't run a web browser, for example, on this. These are meant to be for scientific applications or machine learning applications, whatever, right? Whatever require that last 1% performance. These are meant for those sort of applications. And the big thing is that, of course, this entire part is hardware offloaded. Okay, all the way from the transport layer to the physical layer, mostly is hardware offloaded. Okay, it's not entirely true. I mean, there are some network adapters still that do a part of it in software, but just future looking, right? In the next 5 years, everything is going to be hardware. Okay, everything is going to be implemented in hardware. And for some network adapters, like the Mellanox InfiniBand, this is already true. It has been true for the last 15 years. Okay. And newer generation adapter is going to be true for everyone. Okay. All right. So 11 minutes. Okay. Okay. So let's quickly look at the state of the network API. I told you that the API, the way to access the network, is a very low-level interface. Right? It's performance. Performance is king, right? Not productivity. So, but every network adapter that came out, every vendor who came out with a network adapter had their own API. Okay. Some examples over there. InfiniBand had their own thing called verbs. Mellanox had MXM, IBM PAMI, whatnot, right? Some recent efforts have been made to standardize these into a single unified API, so all networks can use. Unfortunately, there are 3 different standards for unifying all the APIs, and maybe more are coming up. But so it's needless to say it's not been unified yet, but at least there are 3 prominent unification APIs, quote unquote, that are there right now. One is the Open Fabrics interface, also called as libfabric, if you heard of it. This is an effort from Intel, Cisco, and so on, which is a low-level interface. The way it's built is that it allows each network to say, here's like a huge laundry list of features that all potential networks are capable of. Each network says, in this list, I can support feature 1, 2, 5, 16. Okay, another network will say I can support feature 1, 7, 15, or something like that, right? Each network can pick the set of features that it provides, and the application, the user, has to say, oh, these are the set of features I have, how am I going to use it? Okay, something like that. There's another effort called UCX. This is mainly from Mellanox, IBM, Oak Ridge, and so on. This is also a unification API, but it's slightly different. It provides, the philosophy is that I will provide a unified API, either that's implemented in hardware on some network adapter, or it's emulated in software, okay, on the network, but it will provide that API on all adapters, okay. But which one is better? It's unclear. They both have their own philosophical points, but they exist. The third one is it's more of a it's come out of Sandia. It's called Portals 4. It's more researchy in some sense, but there is at least one company that picked it up, the new Bull Interconnect, which is BXI. They picked up Portals 4 and implemented their network based on that. Portals 4 is different from the other APIs in the sense that most of these APIs come from the application point of view. As an application needs these features, how am I going to implement it in hardware? Portals 4 goes the other way around. It says that here is what the hardware can provide. Okay, here's what I can do fast on my hardware, and you figure out how you want to use that for your application. Okay, I mean, we're talking about performance over here. We're not talking about making it easy or anything. It's just how fast can I go? So that's a valid way of thinking about it as well. Anyway, so these are the different APIs that exist today. And in order to communicate, we have a slightly different model in TCP/IP. People who are familiar with TCP/IP programming, you open a socket and you dump data into the socket, and the data eventually gets transferred over the network to the receive side and so on. In these faster networks, the data transfer model is slightly different because it's more tightly integrated between the processor and the memory and the network subsystem. It's so tightly integrated that you need to essentially spoon feed the network a little more closely. Okay, you have to be more careful, but in doing so, you can allow the network to gain more performance. So here's just an example. So if you want to send data to the network adapter, before any communication is done, the advantage over here is that I don't have to copy my data into some socket buffer, okay, into some TCP buffer. I can just say that here is my user buffer, and just send the data out of this user buffer to that user buffer, okay, something like that. I can do that. But if you remember MS-DOS from very old days, MS-DOS used to allow that, and it was a disaster, it was a security disaster. Okay, so because anyone could access any memory, and it was whatnot, it was horrible. Newer network adapters want to give that capability. I want the network to be able to say that I can access this buffer directly, but I want to do that in a more secure manner. So they use this model called as memory registration, where the process goes through the operating system to tell that I want to declare this part of my memory as available for communication. Okay, then the kernel does some stuff. It does some virtual to physical translation. It does pinning of the data and creates a key for the security and whatnot, and puts it on the network adapter, including a translation of the virtual to physical address. The network adapter says, okay, it's all good. I understand this because the operating system, which is secure, told me that this is a valid thing to do. Check. I will tell the operating system back. Then the operating system tells the process that, okay, your registration is done. Once the network registration is done, which is secure, I can directly transfer data from my user buffer onto the network adapter. So there's no copy going on in the path. I'm just directly transferring my data. It's going directly from the memory to the network adapter, going out onto the fabric. Okay? And once you can do that, you can do all sorts of communication. This is a send-receive model that we'll talk a little bit more in the MPI session tomorrow, but here's just a quick example of how it works on the network itself. Okay? On the network adapter, we have the network adapter is directly accessing memory now, okay, because it's so tightly integrated into the processor memory subsystem that it can access the memory directly. And the receiver says that here is a buffer that I want to put the data into. Here is my memory segment that I want to put the data into, and here is the information about that. And the sender says the same thing. Here is the data I want to send from, and here is the information about it. The network adapter hardware can directly access this memory and send it out onto the network adapter and place it on the receiver network adapter, receiver memory subsystem. Okay, all this is happening in hardware. Okay, important thing to note over here is that the processor only told the network adapter where the data needs to come from or go into. It did not actually move the data. The processor was not involved in moving the data itself. Okay? The advantage over here is that whether you send 1 byte or a gigabyte is the same amount of work for the processor. It's just telling you that here is the buffer and here is the amount of data I want to send out. Okay? It's nothing to do with the size of the data. All of the processing with respect to the size of the data is happening in hardware. The network adapter is taking care of it, which makes it more efficient, more scalable in some sense. Okay, the data actually has to go to the network memory. All right, okay, I'll skip all this stuff. You also have, because the network hardware is handling all this capability, you also get this neat capability called as RDMA. How many of you have heard of RDMA? Everyone, right? Hopefully. Oh, half. A third. Okay, RDMA, Remote Direct Memory Access. Okay. When I said send receive, on the sender, the data is being transferred. The sender network adapter is taking the data directly from memory, sending it on the network. The receiver network adapter receives it. The receiver tells the receiver network adapter where to put the data, and then the receiver adapter puts it. In the RDMA technology, Remote Direct Memory Access, also known as put-get technology sometimes, it's slightly different. The basic data transfer is still the same, but instead of the receiver telling you where the data should go to, the sender tells where the data is coming from and where the data is going to. So sender tells both pieces of information, and then the sender side network adapter takes this data, takes this information, takes the data, and goes and directly puts it on the remote network adapter. Okay. So just to compare between your send-receive model and the RDMA model, in the RDMA model, the target side processor is not involved at all. It's not doing anything at all. Okay, the sender's origin side is doing more work. In send-receive, you're doing both sides are doing a little bit of work. Okay. Apart from this, you have atomic operations too. I'll not go into too much detail because I'm running out of time. But atomic operations are like RDMA, except that you're doing like a compare and swap or a fetch and add over the network. Apart from that, they are very much like an RDMA operation. Okay, all right. Okay, so network protocol specialization is the focus today. As I mentioned, offloading, you're offloading more and more stuff onto the network hardware, so the network hardware can do more things, okay, than before. Okay, network hardware can do, congestion control, it can do reliability, it can do flow control, it can do a lot of stuff. But there is more stuff that people are pushing onto the network adapter. For example, for MPI communication, things like tag matching are being pushed onto the network adapter nowadays. Okay, and the Portals network, the Bull BXI network, not BMI, BXI network is already providing this capability. And newer network adapters in the future are expected to provide that as well. For example, Mellanox has announced that their next generation adapter is going to support, or actually the already released adapter supports message matching in hardware. Okay, so that's expected to be the future. And more features are going to be offloaded in hardware. This is not the only thing. All right. Quickly moving on to the second piece, which is network topologies. Okay, so here we talked about how am I getting from the memory to the network adapter. I'm still on the node, right? I'm still got to the node. Now, once I send it outside my network adapter, where does it go? Okay, so network topology. The basic thing we all need to know about network topology. The first thing we need to study when we talk about network topologies is crossbar. Okay, that's the most fundamental network topology that we should be aware of. Essentially, it's an all-to-all switch. Okay, so everyone is connected to everyone in that switch. It's a crossbar. Okay, it's great for performance. Okay, it's ideal for performance, but it's extremely expensive to build. Okay, because everyone is connected to everyone, which means it's not scalable. Okay, in fact, today's ASICs for crossbars go up to 64 ports, which means you can connect 64 machines all to all. Okay, but after that, it's just not cost effective to build larger crossbars than that. Okay, so we don't build more than that. We build up to 64. I think there are some that do 128, I believe, but not too much more than that. And all communication is non-blocking because everyone is connected to everyone. So if I have P0 talking to P1 and P2 talking to P3, they're unrelated. So they go non-blocking manner. There's no contention that happens. As long as you're not talking to the same nodes, there's no contention. Okay, but it's very expensive to do that. In reality, people use what are called network topologies, some approximation of a crossbar, okay, which is try to simplify the connectivity to save on cost. okay, but you lose some performance. And fat tree is probably the most common network topology that's used. In fact, for all small to medium-sized clusters, fat tree is used. Even for large systems, the coral generation machines at Livermore and Oak Ridge, for example, are still going to use a crossbar, even at that 200 petaflop range, okay? And crossbar, a fat tree, unlike a crossbar, is essentially a tree structure of connecting the switches. The important thing to remember in a fat tree is not an all-to-all connection. It's a pseudo or half all-to-all connection in some sense. So the formal definition is that between all pairs of processes, if every process is talking to some other process, okay, not overlapping but some other process you're talking, then there exists a completely non-blocking path, okay? So you can schedule this communication such that no communication will contend with any other communication, okay? You can schedule it in that manner. So there exists such a path, but not all paths are non-blocking, okay? So in some sense, if I have a global communication picture of who is going to talk to whom, I can schedule it perfectly, but if I randomly communicate with different processes, I might, or in fact I will, have some contention over the network. Okay. That's the newer network topologies, the more scalable, quote-unquote scalable systems are using other topologies such as 3 or 5 or 6D toruses or Dragonfly or variants of Dragonfly, Slimfly, whatnot, are being used for these systems. Now, these are quote-unquote scalable because they're scalable with respect to cost, not with respect to performance, okay? They're scalable with cost, which means if you increase the number of nodes, your network components are going to increase linearly, not superlinearly like a fat tree, okay, or quadratically like a crossbar. So that's makes it more scalable, more practical to build large systems with these sort of topologies. But there's also more sharing, okay, which means if you have two processes talking to each other or two pairs of processes talking to each other, you are very likely to have contention because there's so much sharing on the network adapter, okay? In fact, it's very hard to come up with applications where you have no contention at all. It's very easy to create contention in these sort of networks. So the takeaway for you to remember is that there's going to be sharing in the network. You can't avoid it. It's not cost effective to avoid it, okay? So you have to think about locality. You have to think about communicating in smaller groups, detecting processes that are close to you and communicating with them. Otherwise, it's just not going to scale for these large systems. And programming models like MPI and so on gives you a functionality to do that, but you should use it in order to be effective on these sort of systems. As some performance numbers, I'll skip these because I'm running out of time. But let me quickly talk about the last part, which is the integration of the network with the memory and the processing subsystem. Okay. So most network interfaces today, they are already well integrated into the processor and memory subsystem. They work well with the cache coherence protocols. They understand cache coherence protocols, Messi protocol or whatever it is, and they work well on all modern systems. Okay. When I'm sending data from a network adapter, they take into account that the data might be in cache, it might be dirty. Similarly, when the data is coming in from the network onto the system, they take into account that there might be a dirty byte in cache which needs to be flushed and so on. So I have some pictures over here that talk about this. So again, this is the old architecture, but if you have data that is being sent, if it is not in cache, I'll send it from the application buffer on the memory. If it is in cache, I'll send it from cache and flush it to memory and so on. Receive side, the same thing, when the data is coming in. If the data is in cache in a dirty state, it gets flushed to memory before it's actually put into the application buffer and so on. So a lot of these integration are well thought out already, and they're working well today. And there are newer technologies that are coming up, like direct cache injection, which will improve this integration a little better. So you don't have to go to memory all the time. The network adapter can directly access cache instead of accessing memory, but it comes with its own set of challenges as well. You can't directly use that without having some algorithmic thought to how you would use these technologies. Okay, so just to wrap up, so these are interesting times for networks, processor, memory, and so on. They are all integrated. They're all integrated into this big chunk of chip that has everything integrated on there. And network interconnect technology itself is rapidly advancing, but there are three takeaways that I would like you to remember. More hardware integration is key to removing bottlenecks, okay? Integrating more things into a single chip is important. You can't get away from that if you want to remove these bottlenecks and improve functionality and so on. Offload technologies will continue to evolve as we move forward because offload technologies take that work away from the processors, which are the weaker cores and so on. Having some dedicated hardware is important to do this. And network topologies are becoming more shared as we go forward, which means you have to think about topology. You can't ignore topology anymore. You have to think about locality, topology, and optimize your algorithms based on that. I think that's all I have. Thank you very much. I think I used up my questions time. Okay, one question.
So when we were talking about the memory architectures and how one needs to be cognizant of programming to make these memory architectures more efficiently, the takeaway I'm getting here is to take advantage of these new interconnect protocols. You're going to also have to be cognizant of or program specifically for these new interconnects.
So as an application developer, you almost never have to worry about the direct interconnect capability itself because most programming models, most higher level programming models like MPI or PGAS or whatever, they will hide these capabilities for you and they will give you a common API irrespective of what the network adapter would use. Okay. However, you should pay attention to their recommendations. If they say that you need to use this function to optimize your topology, it's important. This talk will essentially tell you why they are giving you that recommendation. Okay, but you don't have to worry about the network topology itself, but do pay attention to the suggestions they're giving, recommendations they're giving to optimize these things for you. Okay. All right. Thank you.